Around the world, scientists are looking increasingly to the sun as a possible alternative source of energy. In Australia, an unusual source of energy from the sun is being investigated. Scientists employed by the Department of Defence have been encouraged by their research into a revolutionary form of oil, solar oil. The principal defence energy scientist is Dr. David Warren.
Solar oil is the name we give to oil which we derived directly from living plants. Now, some plants store solar energy in the form of sugar or cellulose, but there are others which have the happy knack of storing it directly as hydrocarbons. The sample I have here was obtained from a floating microscopic alga or water plant which could be found in almost any Australian lake or swamp, Botryococcus. It occurs either in a green form or sometimes in an orange form. The main difference between solar oil and mineral oil is that our mineral oil comes from reservoirs under the ground which were built up millions of years ago, and when we've used them up, they're gone forever. Solar oil, on the other hand, is being formed all the time the sun is shining on the plant, and all we have to do to obtain more is produce a new crop.
Per head, Australia is the world's second biggest oil consumer, and its consumption rate is growing alarmingly. At the moment, other countries outside the oil-producing Middle East pay about 3 times more for their oil than Australia does. Since about 70% of its needs come from Bass Strait oil wells, Australia so far has been largely insulated from the world energy crisis.
But this can't go on, because we know that over the next decade, the production rate from Bass Strait must tail off. It is now approaching the half-empty point. And if our demand continues to rise, and it's doing so at the present time, we are faced with an expanding import bill from $1 billion up to $4, $5, even more billion dollars. At that state, it's doubtful whether we can economically stand the strain. Certainly our living standards will fall. And defence-wise, we find ourselves extremely vulnerable. Like any other modern nation, our defence equipment runs exclusively on oil. Tanks, trucks, boats may run on substitutes, but not as efficiently. Planes have no alternative. In the meanwhile, we hope to find more oil. Geologists tell us that there's an even chance that we may find another Bass Strait. But even if we could get 200 wells a year being drilled as we used to in the old days, instead of the 20 or 30 we now have, over that 8 or 10 years, it's unlikely whether there will be one drop of extra oil in anyone's tank because of the time taken to bring a field on stream. And if we don't find oil, then alternative sources such as solar oil are going to seem far more attractive.
It was in the Coorong district southeast of Adelaide that Australia's first oil fever developed. Ironically, it was the alga responsible for solar oil that inspired the first drilling.
Back in 1852, in the heyday of Australia's gold rush, members of a gold escort were looking for horses here in South Australia near the Coorong. In a dried up lake bed, they came across some rather strange material. It was black, flexible, combustible. It burnt with a yellow flame, and when it did, it smelt like tar. They called it Coorongite, after the district in which it was found. At first, people thought it was bitumen. And if it were bitumen, it meant that there was some source of oil nearby which had leaked into that lake. Now, to confirm this, they picked up 20 tons by hand and sent some to James Young's oil works in Scotland, where it was distilled and gave very useful lighting oil. With that sort of evidence, the entrepreneurs set up the Salt Creek drilling company, and Australia entered its first bout of oil fever, of which there have been many since. And here they drilled Australia's first oil well in the Coorong on a dried lake known as Alf Flat in 1892. The wellhead casing is still here after 80 years. Those pioneers drilled to 300 feet in their search for the oil and found nothing but shells and seawater. Undeterred, they got further equipment and drilled a second well to 900 feet and still found no oil. The enthusiasm of the search continued for 2 more decades before scientists in laboratories found that this material which had started off the search was not mineral at all. It was the remains of a freshwater plant, our friend Botryococcus, which had grown in profusion on this area when in flood time it was a lake, 2,000 acres in area and up to 20 feet deep. The suggestion was made that perhaps the plant itself could be grown as a source of oil. But at about this time, oil was becoming abundantly available and at a very cheap price from the fields in Arabia. Hence, all enthusiasm for this new approach died. Long before the oil price rises of 1973, energy scientists were considering alternate fuels which we might use for when oil runs out. My colleague Dr Lance Hillen, when he read of the Kurungite story, felt that here was a possibility which, no matter how remote, must be looked at.
Delving into the scientific literature, I found that in 1968 this plant was reported containing up to 70% liquid hydrocarbons. Back in the 1930s, it had been connected with the formation of these New South Wales kerosene shales. It was also known that the plant was responsible for these rubbery deposits on intermittent lakes, such as at Alf Flat in South Australia, and that this material was the peat stage of these Turbonite deposits. Taking these facts together, it was quite obvious that at a time when Australia's indigenous reserves were to be seen to be running down, that in fact this was a plant that was worth more than just a superficial examination.
Turbonite, the fossilised alga, provided Australia with an important source of oil in World War II. It was mined at Glen Davis near Bathurst in New South Wales. Today, the weathered and derelict Glen Davis refinery is the only evidence of this wartime oil resource. Commonly known as kerosene shale, Turbonite produced an adequate but primitive fuel. The extraction of oil from kerosene shale proved a costly process, and operations ceased soon after the war. Although useful deposits of the fossilised fuel remain, recent research has concentrated more on the living alga itself. In the Darwin River Dam, the alga has grown so prolifically that it's caused drainage and other problems. Local authorities have found up to 3,000 tonnes of the plant, which is known to exist throughout the world in varying conditions and climate. Scientists are keen to discover its biological secrets. Dr Lindsay Wake is a marine biologist with the Department of Defence.
Botryococcus is a microscopic alga, mainly green, although it can occur in a red form. It's a colonial alga. In fact, the word botryoidal, in its name Botryococcus, means grape-like. Under the microscope, it resembles a small bunch of grapes. On occasion, it can give rise to massive blooms, although what triggers bloom formation in one water body and not another is not known.
The Botryococcus alga displays some unusual qualities. Its ability to store hydrocarbons directly in a process from sunlight makes it unusual in the plant world.
Most plants store the sun's energy via the photosynthesis process as sugar, as in sugarcane, or as starch, as in the potato. There are, however, another set of photosynthesis reactions which lead to the formation of hydrocarbon. Botryococcus is rather an unusual alga in that it chooses to use the hydrocarbon pathway to store the sun's energy. To achieve this, it requires a large body of water, a supply of minerals, the essential nutrients, phosphorus and nitrogen, carbon dioxide from the air, and sunlight.
A distinct advantage of solar oil is that it can be extracted from the alga by a relatively simple method. The oil is separated from the plant base by adding a solvent. The mixture of oil and solvent is heated, and the oil is then separated from the solvent by distillation. The resultant liquid is solar crude. At the CSIRO Applied Chemistry Division in Melbourne, tests on the solar crude have produced encouraging results. A mass spectrometer has analysed the molecular structure of the oil. The basic quality of the solar crude has proved to be as good as mineral oil. However, tests have shown that it has to undergo a special refining process, hydrogenation. Hydrogenation has been carried out at the BHP research laboratories in Melbourne. The refining process is necessary before the solar crude can be converted into the familiar transport fuels, petrol, kerosene and dieseline. Defence scientists at the Aeronautical Research Laboratories point out that this process is available with existing technology at oil refineries. Dr Hillen is particularly optimistic about the potential of solar oil as an alternative fuel.
Analysis of this liquid shows that it contains 67% gasoline fraction, 15% aviation turbine fuel, 15% diesel oil fraction. The actual proportions of these fractions can be adjusted by varying the conditions of the cracking process. The individual components of this oil are the same as those found in fuels derived from crude oil. Notably absent are aromatic hydrocarbons. Aromatic hydrocarbons are unsuitable for use in aviation turbine fuels. Thus, solar oil is a potential alternative source of aviation turbine fuel, which is a major proportion of defence fuel needs.
Despite the optimism, there are problems to be solved before solar oil can be regarded as a real alternative.
Research will be needed to enable us to selectively grow Botryococcus and not some other plant. While we do not yet understand the factors involved, the growth of Botryococcus for 3 years on the Darwin River Reservoir suggests that a monoculture is feasible. Likewise, the size of the Darwin River Reservoir, 4,000 hectares, indicates that the plant can be grown on a large scale.
Most of the problems are biological. There's a lack of information on the alga itself. Scientists need to discover the conditions of temperature, light, water and other factors that produce optimum growth. Water samples from Darwin have been tested at the Defence Materials Research Laboratories. They have provided some of the answers, but more detailed research is needed.
At this stage, the productivity of the alga in the Darwin River Reservoir appears to be limited by the levels of phosphorus and nitrogen. However, here we are measuring the levels of all of the parameters in water bodies in which Botryococcus grows. We're measuring the metals, the trace elements and the nutrients. It's an attempt to correlate with the growth of the alga in one water body and not another.
The question that everybody asks, of course, is, can oil be made economically by this process? And that's a question which we cannot answer yet. There are still so many unknowns. In Darwin, we have 2 reservoirs. Botryococcus grows rapidly in one and is hardly to be found in the other. We're not quite sure why. We have to look at the problem as to whether Australia's water resources, and we're not well endowed with water resources, whether they could supply the evaporation rate on our tanks. We're not sure yet whether if we cultivated a pond of Botryococcus, whether some other alga would so enjoy the nutrients that we'd given to that pond that it would take over and perhaps not produce any oil. We might wonder whether we could harvest it economically. We think we could because we're lucky that it's a floating alga and because nature brings it to the surface and we can use skimming methods which are much easier than trying to remove it from a very large body of millions of tons of water. Now, those are the questions which we still have no answer. Some we have answered. Dr. Hillen has already shown you that we can, from our raw solar oil, produce present-day acceptable fuels. That we do know. The question is, can we get it to grow at the rates we would like it to grow? We might be discouraged by some results, except we know that it has happened in nature, and there must be an answer. Could we produce oil in sufficient quantities? As a rough indication, we have calculated that if we could put the largest natural lake in Victoria under cultivation and achieve the estimated growth rates that we know from other information, then we should be able to produce about 2% of Australia's oil requirements, which is the amount that the Defence Department would use in peacetime, or if you like, about half our aviation's fuels requirement. How quickly could we do this? We don't expect to do it quickly. There is a lot of work to be done, and we foresee that Botryococcus oil or solar oil is likely to be one of those alternatives which may come to our aid when oil becomes very scarce. We have other hopes in oil from coal, oil from shale. We know they're all going to be more expensive than oil as we buy it today. How much more each of those is more expensive, we still cannot accurately estimate. But we think Botryococcus is a contender that must be looked at.
But if there's still a...
Last weekend, the Saudi Arabian oil minister, Sheikh Yamani, predicted the current crude oil price could